Mi amor no tiene esperanza.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So we said that the Schrödinger wave function can be solved for one-electron atoms. But for non-hydrogen atoms, basically multi-electron atoms, these have additional factors that affect the electron energy. And so the first thing I wanted to talk about is the electrostatic, or Coulomb, potential energy. And this is proportional to Q1 times Q2 over R. What this means is that the Q represent two separate charges, and R is the distance between the charges. So now, if you have the positive nucleus here, and you have more than one electron, let's say 1, 2, and on the outer shell we have 1, 2, 3, 4. Now we have to take into consideration the electrostatic potential energy, which is proportional to two charges and the distance between them. So now each of these electrons are interacting with one another, and they also feel repulsion since this guy is negatively charged and this guy is also negatively charged. This guy is negative, this guy is negative. So the interactions between electrons must also be taken into consideration. Also, the inner electron basically shields the outer electron from electrostatic attraction of the positive nucleus. So if you see this diagram right here, where electrons further away can be ignored, but if this is the electron of interest, electrons in between the positive nucleus and the outer electron of interest will shield the electrostatic attraction. This results in an effective nuclear charge, which is written as ZF. And the equation for effective nuclear charge is Z, the nuclear charge from the nucleus, minus the average number of electrons between the nucleus and electron of interest. So let me show you an example of this. So neon, if you look on the periodic table, has 10 electrons. What this means is that the inner shell contains 2 electrons and it has 8 valence electrons. So let me draw you a picture of neon really quickly just to show you that. 2 electrons in the inner shell and then 8 electrons in the outer shell. We'll go over how to draw these structures later on when we talk about Lewis structures. But basically, we have 2 here, A here. This is a noble gas. So when we do the ZF for neon, we have 10 electrons, or nuclear charge since we have 10 protons, minus 2. And this is the average number of electrons between the nucleus and electron of interest. So if we want to look at this electron, it has 2 electrons in the innermost shell that's blocking it. So we end up with a charge of plus 8. Now let's look at F minus. So for fluorine usually has 9 electrons, but since this has a negative 1 up here, it means that it has 10 electrons, 1 extra. So it has the same number of electrons as neon. So for fluorine, we write out the effective nuclear charge as 9, since that's the atomic number of fluorine, minus 2 in the innermost shell. And we end up with a value of plus 7. The last example I'm going to give is sodium, but in this case I want to look at sodium plus. So sodium usually has 11 electrons, but since there's a plus sign right here, it lost an electron. And so we have 10 electrons again. And the effective nuclear charge of sodium plus is 11, atomic number of sodium, minus 2 electrons in the innermost shell that's shielding it, and you get plus 9. So what this is showing us is that although each of these have 10 electrons, but the effective nuclear charge varies because each has a different atomic number. The sodium cation has the largest effective nuclear charge, right here, which results in the electrons being held the tightest and therefore the smallest atomic radius. So later on we'll talk about periodic trends, and the trends arise from the charges that each of the different electrons feel. So finally, p and d orbitals have a nodal plane that we talked about before, right? So for example, if I have a p orbital, it has a node right here where there's 0 electron probability. On the other hand, s orbitals, which have a symmetric distribution around the nucleus, have no nodal planes. This results in different electrostatic interactions between the nucleus and electrons in an s or p orbital. So between these two, they have different electrostatic interactions. And thus, s electrons have a lower energy than p electrons even if they're in the same shell. And that's why when I drew out the atomic orbitals, I showed you that the energy increases as you go from an s to a p orbital.